Okay, so let's yeah, I think it's better we go here. Then it will show as a input portfolio df dot log portfolio I. Then what we will see. So let's try to run that statement. Put multiple values for all equals to 1. Oh, this norm only takes one function. So it should do this, not the other way around. So norm does not do the dot product. It only takes it returns the absolute value of the summation of the elements inside a vector. So I think that's okay. So now that starts to work. So that's good. But I actually just wanted to point out, right? We also need to be very careful about where you put these values, in various places. So for example, this is not that time-consuming either, so you can do things like this. This will make sure that the return row is non-zero when it's non-nan values. Okay, so maybe this code refactoring is already functional. So let's go ahead and see what happens if we run this. What we're looking for is to verify that the code logic is the same as before. So, and hopefully it runs faster than this function. So we'll see. Right? Positions. Like we'll get warnings because we're dividing by 0, but that's okay because later we do this operation to make sure everything's fine. Okay. So interestingly enough, our code is actually correct, and we ran it about 4 times faster. So what happened was basically we're doing a lot of the data preparation ahead of time. So they're all together inside the memory space instead of being scattered around in multiple places inside this Python dictionary. In the previous implementation, we will have things like this eligible rows attached to the original data frame, but they are everywhere around in memory. But instead, we create a data frame and make sure they are all put together in contiguous blocks of memory, and then we prepare them and return and yield them together to generate. So this is like a generator, the data that we need throughout the entire backtest. And then instead of having multiple for loops and making calls to .add inside a nested for loop, we do all of them in vectorized operations while using the division by eligibility masks, right? So we did division by eligibility masks in order to get, remove those values that we're not interested in. And then we use this nan to num function so that we can still work with operations that can handle these nan values at critical points. So imagine if one of our value, for example, if one of our positions were nan here, and then when we do norm, which is basically summation of the absolute value of the components, you're going to take a floating point, and then we will add it to a nan value if we didn't have this line. So this will give us nan value to nominal total, and then divide by a nan value, and this will throw off the entire computation. Instead, because we are protecting the arithmetic computations with by switching out to 0 at appropriate times, we managed to skip the entire for loop altogether and only have one for loop here, right? So inside the PNL computation, we also skip the for loop, and our logic is the same. So since we verified that's correct, I think we can remove this, right? I think we can now remove this old alpha class, right? We don't have this. We don't have to have this PNL stats. We can remove this, right? And then we can have this as the main implementation. So let's put that over here. And then let's replace the old PNL stats computation with the new PNL stats computation. Right, so let's go ahead and put this over here. And everything should work as expected. We will rename this to alpha, which means inside utility function, we can go back to an alpha class and use the original function like this, and we don't have to do much. So everything should work as expected. And now from 360 seconds, we got our runtime down to 20 seconds. So I think this is a good point to stop here. We did a lot of refactoring, so we're going to save this as set number 6. Hopefully you've had no problem following along, and I will see you in the next lecture. So go here. You don't need simulations, you don't need any of these, you don't need the code, you don't need this. 1, 2, 3, intro, main, 10. So let's put that inside set 6, right? And let's continue. Okay, so now that's all done. Where can we do better? Right? I mean, we always want to do better. So let's take this time me function and then put that inside here, time me, and see how long it takes to do that. You know, we already have that inside the util file. We already have that here. I think what I want to do is maybe profile this thing. So let's go back to Python tree-m comprof. What's that? -m comprof -l -b, and we'll run main py file and see exactly which of these lines are problematic inside the code. Right? So code is still fairly simple. And a lot easier to read now because it's just mathematical computations one by one. But where is the performance bottleneck? So let's take a look at this. So now 50% of the time is spent inside this compute meta information function. And then 10% of the time is created in generating the data. And then 3% is spent here. PNL computation. So that's interesting, maybe a little bit interesting. About 60% of the time is spent doing that. So how do we shorten the time? So let's go and profile these two functions. So compute meta info. Let's also go and do the PNL computation. Right. So let's profile these two lines again. So that's actually something already very interesting about these lines, right? If you look at this if you look at this kind of mathematical computations, very interestingly, it only takes us 4 seconds to do, but somehow this line only takes us about this 4 lines takes us about 8% of the time, and this is taking us about 6%, 7% of the time. But that's quite surprising. Because NumPy should be pretty fast, right? When you're doing vectorized computations, there is no reason why it should be taking so long. So that's quite puzzling. Like we know why this is taking so long, because it has to, you know, basically loop through the thing many times, right? It has to loop through the thing that many times in order to perform this line. But in this case, this is very intriguing, right? So how come this simple statement takes up 6% of our time? So let's take a look at these operations, right? How about we go there and then we print out what these arguments are made of. Then it will help us to understand exactly where to work on. So you see, surprisingly, these two middle rows didn't take as much time, but these last two multiplications took really long relative to the whole program. So let's go ahead and print out what exactly these are. So print positions, print forecast chips, or target, for row, and let's take a look what these are. So we're just printing out what all of this. We already know this is a real number, so a float. But why are they taking so long, right? So that's interesting. Okay, so we printed them out. So for some reason, right, positions happens to be a Panda series, and then forecast is a NumPy array. And the forecast chips is a float. Full target is a scalar, and then volatility rho is another Panda series, and then closed row is another Panda series. So no wonder, I mean, we're taking multiplications of the NumPy and then taking it to a Panda series. So what do you think happens there? In order for two operands to be compatible, that means the functions that we're calling has to do with implicit what do you call typecasting, right? But this isn't good. What we want to do is just to do the pure mathematical computations. Like inside this Panda series, we always follow the same format. We go from in alphabetical order, right? It's not like we are evaluating. Like even if we go to the whichever index this is, we don't need, because we have this self.instruments, and we don't ever change the ordering of the instrument inside the list, we don't actually need this column. Okay, we can do away with this and just deal with the values here. So what happens if we just, we move that across all of our computations? So what if we take this, right? And then, so what if we just return the underlying NumPy array instead of the entire Panda series? Then what happens? So let's see where we are using the statements. And then it's inside the portfolio. Okay, so we're going to return back values here. So what happened if we return the NumPy array instead? Then now our computations will be a little bit different, right? So if you're returning NumPy array, then all of this are going to be, this is going to be a float, this is pandas. I mean, this is a NumPy array, and NumPy array. So let's see how that performs. So we're comparing it to this, we're comparing it to this original profile. So if you take a look at this line here, then we go to main.py, and I just put this over here. And then let's go back to the utility file and say we want the profile. This run simulation function, and then let's see how long that takes. So let's remove this line. So inside the previous run simulation, a very simple operation like this took about 7% of our time. Now we go back to the newly profiled run simulation function, and you see that the same line of code takes up less than 1% of the time, right? And even these lines, because we're not calling NumPy functions on Panda series, and we are only working inside the NumPy array. It turns out we compute much faster in each of these operations, and including statements like this, with equal positions times closed row. If you compare it to this, we take 0.1% compared to 6%. So that's very interesting. And so now we basically have not too many dominating factors in terms of time complexity except for this. So inside the run simulation function, 70% of the time is spent inside this line. So we can basically just focus on that, right? So I mean, we'll just delete this, right? But I hope I got through the point about even though we can work with both Panda series and NumPy arrays, we want to use the one that is most likely. Well, that will help us do the computations as quickly as possible, right? It's important, and you may think it's very trivial, but you're saving 20% of your time there. So that is the importance of being aware of what data types you're passing around. So let's remove the profile and see how long this takes. Okay, so let's run this. So now instead of 21 seconds, we should have cut down some of our timing. And we run it in 13 seconds just by making sure that the data types is NumPy instead of pandas. And this as well, compare this to 360 seconds. Looks like we're doing much, much better. Okay, now let's look at the profiling and see where we can then improve our code. And we go inside this compute meta information. So I hope you can see where I'm getting at, right? What I'm saying is I want you to understand which part of the code is causing the problems by profiling. So first you profile for the function calls, then you see which function calls are really causing the issue. Then you can drill down specifically to that function call using a line profiling. So you profile the function in more granular detail. Then you can see which lines are causing a surprisingly lot of time. And then from there you can say, am I using the correct data types inside this line, inside the lines that are taking surprisingly a lot of time? And then maybe you can fix the functions, or you can look into the internal implementation of the libraries that you're calling, which takes a lot of time. And this will help you to go towards a much more efficient solution. Again, if you want to look at a lot more interesting profiling, you can either read the full paper that I uploaded, or you can check out the book. They have a lot of interesting examples. So let's look at this function. Here, there's not much that is left for us to do, except maybe you're spending about 30% time inside the post compute. So are we doing anything inefficient inside post compute? I don't think so, right? I mean, the focus is always to is on the core of the algorithm, right? This you don't, like, it's okay if you don't optimize this alpha 1 class, because you're always going to be using this one, but you're only going to be using this code logic for this particular alpha. So your focus is always to make this common code block as efficient and powerful as possible for our quant alpha research cycle. So 82% of the time was spent inside this z-score function. Okay, so what can we do here? What can we do inside the z-score function? Is it when we do apply, right? We're going to go through each of the rows, and then we're going to create new pandas. So okay, we can try applying it to the underlying NumPy data, right? Because this will now receive a NumPy array, so this should make it significantly faster. But as you can see, right, it's getting more and more difficult to find these cheap wins. I mean, of course, you have 12 seconds. If you want to shave off another 6 seconds, that's like half of the runtime. So it gets increasingly harder to do so. So you should take it with a pinch of salt. Just optimize until it's good enough, and then just it's okay to stop once you got to some point, right? Now we have shaved these significantly slow operation and got it down to something that is relatively quick, right? So that's, again, a very quick win. We just added these two statements, and you got a quick win. Okay. In the paper, we also talk about multiprocessing and using multiple cores. Maybe I'll go into that in the future lecture series. I think that we are getting quite close to a good, efficient code already. So I might want to stop here. Let me just do the profiling one more time, see how long that takes. Maybe I'll just add on one more lecture. We can still make it a little bit faster, right? For instance, we're still calling this lines. So okay, anyway, we got this down to 10 seconds. So that's pretty fast. So anyway, I'm considering to just stop here, or maybe I will create a last lecture to sum up what we have learned so far. For now, yeah, there's nothing much I want to include yet, so I'll either see you inside the 201 class or inside the concluding lecture for our lecture series.